What's up, guys? So, the very first page of Chapter 17 lecture notes, it has a link for you to follow. That link does not work. However, I've gone and I've found the link. They just updated it. It's up here at the top. If you can read it here, go ahead and type it in and go there. I'll also have this same link attached in the course description, or the description of the link on Blackboard that you just clicked on for this lecture video. So under the little description thing, you should be able to find this link. Also on YouTube, where this is hosted, I'll try to put it either right there underneath the description there, or in the comments below. So hopefully you should be able to read this. I've got it in 1080p, so it should be pretty clear. You should be able to read the website there and type it in. Go in there, watch this video, fill out the first page, and now we're going to get started on the actual lecture notes. So you should be able to work your way through the first page. All that information is in that lecture video. Once we get to the second page, we start talking about sampling distributions, which is exactly what they talked about in that video. The sampling distribution of a statistic is the distribution of the values taken by the statistics in all possible samples of the same size from the same population. Okay, it's what all possible samples of size n would look like. We've got three types of distributions. We got a population distribution, a samples distribution, and a sampling distribution. So let's look at the differences between those two kind of in graphical form. A populations distribution is what the entire population is overall. So if you think really simply, maybe in colors, we'll do colors of marbles here. So you might have 100 blue marbles and 100 red marbles in your entire population. Okay, if I take a sample of, say, size here, size n, of those marbles, I might wind up with 12 blue marbles and 8 red marbles. Or if I take another sample, I could wind up with 9 blue marbles and 11 red marbles. So each sample you take can have a different percentage of red or blue, but the overall population distribution is always going to be that 50-50 percentage. If we take all samples that we could possibly take out of this entire population of all different combinations and everything, that's when we get our sampling distribution. So we take every single sample, we plot this sample in here, we plot this sample in here, we plot this sample in here, and we do it every time for every single possible sample that we could take. That's how we get our sampling distribution. And you should kind of gotten some of that stuff in the lecture video. If you want to work with, if you like doing models and stuff on the computer and you like to do little apps and stuff, this is a link for that. If you're not interested in that, this is not something we're going to have to be tested on or anything like that. It's just for people that like to get interactive. You could try it. If you don't want to, fair enough. On page 3, we get into the meat of the lecture. So theorem 1 says x is approximately normal, mean mu, standard deviation sigma, then x bar is approximately normal, mean mu, standard deviation sigma divided by the square root of n. It says if the underlying distribution is normal, then x bar is also normal. So if something is normal, the mean of its distribution is also going to be normal. So what we're really looking at is we're going to distribute just like we had up here. Okay, so in this, let me see if I can find it. So if we scroll up, okay, this doesn't look normal, but this turns out to be normal. That's theorem 2. We'll look at it in a second. But if your initial data is distributed normally, it's always going to be distributed normally in the sampling distribution. Okay. However, sometimes we don't know what our initial distribution is distributed, and sometimes we know that it's not distributed normal. So the central limit theorem for population means says that if the shape of the underlying distribution x is unknown, but its mean mu and its standard deviation is sigma, then the mean of that distribution is normally distributed, and it's distributed normal, mean mu, standard deviation, sigma over the square root of n. Basically, if we don't know anything about the shape of the underlying distribution, we can still say the distribution of x bar itself is normal if the sampling values have to be independent, they have to be random, and the sampling size has to be large enough, meaning n has to be greater than or equal to 30. If those three things hold, we can say it's normal. Now we've got some examples here coming up, and I'm going to take it over to the whiteboard to do those examples. So bear with me real quick. Pause if you need to pause, and we'll get right to it. Alright, first example. It says a fish hatchery releases rainbow trout in certain lakes when they reach around 450 grams. The trout are raised in a large swimming pool style tanks and are all put into the same tank when hatched so that no fish in a tank is any older or younger than another. Typically, they all reach the desired size, 450 grams, around the same time. Assume that the size of the trout are normally distributed with an average of 450 grams and a standard deviation of 12 grams. Part A says, using the correct notation, give the distribution of the weight of the trout in the tanks around the time of its release. Alright, so the first part for A, it says right in the question that they're normally distributed. That means that X is approximately normal. The mean was 450, and we said that the standard deviation was 12. Easy enough for the first part. We hadn't taken a sample size, we're just talking about the data in general. X is approximately normal, says it directly in the question. Means 450, standard deviation 12. We look at part B. You've got your lecture notes, you can follow along. It says, can we say that the sampling distribution of the mean of X is normal if we're using a sample size of 16? If the data is normal, we can say that the sampling distribution is normal. It doesn't matter what the sample size is. If it's normal, it's going to stay normal. So yes. Yes, we can. It is normal. Okay. Give the sampling distribution of X when the sample size is 16. Use proper notation. That's part C. So we determined the sampling distribution when size 16 is normal. Now let's give it. Okay. X approximately normal. Mean 450. Standard deviation. We got to do that 12 over the square root of 16. Okay. We're going to want to simplify that. So X is approximately normal, 450, 12, square root of 16 is 4. Like I said, we need to simplify it. X is approximately normal, 450. 12 divided by 4 is 3. So what we're looking at is our sampling distribution. Need to have an X bar here. X bar is approximately normal, 450, 3. That's it. Make sure you put the bar on top. If you don't put the bar on top, you're going to get it wrong. I know we're not in class. You're not going to be doing a whole lot of stuff by hand. But keep track of this bar. This is the entire distribution. This is the sample distribution. So we need to keep track of that average. Alright? Let's look at D here. D says, suppose you are asked to find the probability that the weight of a randomly selected trout is between 440 and 455 grams. Using the correct notation, give the distribution that you would use. Okay? We need to determine about a randomly selected trout. That's just one trout. We only picking one. We ain't picking 16. We ain't picking 35. We're picking one trout. So we don't need to use the X bar distribution. We just need to use the regular distribution that we started with. We're picking one trout. Alright, so what we're looking at here, the distribution, says correct use notation, use distribution that you're going to use. So D, I'm going to say X is approximately normal, 450, 12. That's the distribution that we're going to use. Okay. C or E says use the proper notation to write this probability statement, give the calculator command, and compute the probability from part D. Alright. Let's look at this. E. We're looking at the probability. Okay, low side is 440. Alright. Less than, it says between, right? Less than or equal to X is less than or equal to 455. Okay. Now, calculator command. Here's where it gets a little different. I'm going to show you how to use your calculator. Okay. It's going to go normal CDF. Alright. When we do normal CDF, we've got a few things that we've got to type in. Let me bring you over here to the calculator, show you the command so it'll make sense. We'll bring it back up here to the board. And then we'll actually do it. I've got my handheld here, but I'm actually going to show you on the computer. It shows up a little bit nicer on the GoPro. We'll flash back up here and we'll write the answer and everything. So We're trying to answer questions D, E, okay, and then we'll get on to F here in a minute. We're trying to answer question E, and I told you I'd show you how to use a calculator. Okay, so we're going to get over here to our TI-84. We're going to go second distribution. Okay, just like we were doing with binomial and geometric, we're going to use normal CDF. Okay, remember down here we were using geometric PDF, geometric CDF, binomial PDF, binomial CDF. Now we're going to use a normal PDF and a normal CDF. Primarily normal CDF. We got normal CDF here. Our lower bound, if we look back at the question, our lower bound is 440, our upper bound is 455. Easy enough. 440. Upper bound is 455. Okay. Our mean here is 450. It was a single trout, so we decided that our standard deviation here was 12. Because we weren't taking a large sample and averaging it. We were taking a single sample from the overall population. So we paste that in, hit enter, we get our percent here. So there is a 45.92%, right? So how does it actually answer the question? So it says, suppose you are asked to find the probability that the weight of a randomly selected trout is between 440 and 455 grams. So the probability that a randomly selected trout is between 440 and 455 grams is 45.92%. Now let's put that on the board so you can see it. So let's finish it on out on the board. We've got probability that 440 is less than or equal to X is less than or equal to 455. We write it in our calculator command. Normal CDF, 440, 455, 450, which is our mean. Our standard deviation is 12 here. If I wanted to put in a sentence, the probability that a randomly selected trout is between 440 and 455 grams is 45.92%. Little aside, if I had decided that I wanted to take and do that X bar distribution instead of the standard X distribution, because we only chose one, it'll wind up being the same thing. Okay, don't feel like you're going to make a mistake there. If I would have said, okay, I need to choose the distribution of X bar to find this for this single trout, I would have said, okay, X bar is approximately normal, 450, 12 divided by the square root of n. Here n was 1. Square root of 1 is 1. So that it would simplify to X bar is approximately normal, 450, 12. You would have got the same thing. So don't worry about it. It's not a big deal. Next question. F says, suppose you are asked to find the probability that the average weight in grams of 16 randomly selected trout is between 440 and 455. Using correct notation, give the distribution you would use. The difference between this question and the last one, we got 16 randomly selected trout. Okay. G says using the proper notation to write the probability statement, get the calculator command, and compute the probability from F. So we're going to complete F and G real quick. Okay. I'm going to go ahead and grab the calculator up. We're right here, right? So I know it's between 440 and 455. So if I go second distribution, normal CDF, it's between 440 and 455, that stays the same. Mean also always stays the same. The only thing that changes here is the standard deviation. The standard deviation has to change to 12 divided by, okay, remember it's the square root of n. Our n here is 16. So, square root of 16. For you lazy folk out there, you can type the square root of 16. You don't have to reduce it to 4 in your calculator. It'll do it for you. It's better to reduce it to 4. It's better to overall reduce it to 3 if you're doing it by hand first. That's great. If you want to be lazy, type it in this way. Be my guest. You're going to get the same answer. Okay. So we'll paste all that in. Hit enter. We get 95.18% if we're rounding. Now let me show you this on the board real quick. Alright guys. So answer to F. We got to show the distribution. X bar, approximately normal, 450. 12 over the square root of 16. We already found that previously to reduce to X bar is approximately normal, 453. Okay, that's our sampling distribution here. For G, probability statement, probability that 440 is less than or equal to X bar, and it's got to have the bar on top of it, is less than or equal to 455. Okay, if I write my calculator statement out, normal CDF, 440, which is our lower bound, 455, which is our upper bound, 450, which is our mean, 3, which is our standard deviation. Type it in the calculator, gives you 95.18%. If I want to put it in a sentence, the probability that the average weight of 16 trout is between 440 and 455 grams is 95.18%. It's that simple. Okay, example number 2. Suppose that we do not know the shape of the distribution of the weight of the trout in our population, but we do know that the mean is 450 grams and the standard deviation is 12. So we don't know if the overall distribution is normally distributed or not. We don't know that at all. A says, can we say that the sampling distribution of X bar is normal if we're using a sample size of 16? Why or why not? Sample size of 16. Now, we've got some conditions if we don't know if the distribution is normal. It's right there with that central limit theorem. You can scroll back up in your notes and take a look at it. One of the conditions is if we don't know what's normal, the sample size has to be greater than or equal to 30. Sample size here is only 16. So, can we say the sampling distribution of X bar is normal if we're using a sample size of 16? No. Why? Because 16 is less than 30, and we don't know that the population overall is normal. I'll write that on the board here in just a second, but let's move on down to D or B so that we can get a few of them up here at one time. Can we say that the sampling distribution of X bar is approximately normal if we're using a sample size of 36? Why or why not? 36 is greater than 30. I think we're okay. 36 is greater than 30 as long as we follow the other two conditions about choosing randomly and keeping it independent, we should be fine. So yes, I'm going to say that we can say it's approximately normal. C says give the sampling distribution of X bar when the sample size is 36. Use proper notation. Let's go on and put all A, B, and C up on the board so you can see it written down. Alright, putting it down in the words on the board for you. Part A, no, because the initial distribution isn't normally distributed. Therefore, n needs to be greater than or equal to 30, but n is only 16, which is obviously not greater than or equal to 30. B, yes, as long as they are also random and independent, those are the two other statements they have to hold. Since 36 is greater than or equal to 30, it's all going to hold. Okay. Now C wants you to write this distribution. So X bar is approximately normal. 450 stays the same every time. Okay. My initial standard deviation was 12. Remember, I have to divide that by the square root of n. Square root of 36. Okay. Now we can simplify that. What's square root of 36? Square root of 36 is 6. Okay. So simplify it. X bar is approximately normal. 450. Square root of 36 is 6. Okay. I can simplify that. X bar is approximately normal. 450. 12 divided by 6 is 2. Okay. So you notice, just looking at it, with our sample size of 1, our standard deviation stayed the same. It was 12. With our sample size of 16, our standard deviation dropped to 3. Our sample size of 36, our standard deviation drops to 2. So the larger your sample size gets, the smaller your standard deviation gets. So you can really, really limit your stuff really, really tight. Keep that in the back of your mind. So we've got A through C answered. Alright, D says, suppose you are asked to find the probability that the average number of grams of 36 randomly selected trout is between 440 and 455. Give the distribution that you would use. Okay. Using the proper notation, write the probability statement, give the calculator command, and compute the probability for part D. Okay. We have already done the 36 part. Right? So, what distribution will we use? We'll use the same distribution that we used in part C. And I'll write that on the board here in a little bit. We can go ahead and answer a little bit of part E while we got me right here at the computer. Okay, we're going to have to write the proper notation on the board, give the calculator command on the board. We can go ahead and compute the probability. We know that it's going to be normal, 450, and 2. We just found that. And I'll write it all up for you so you can see it as well. But let's go ahead over here to the calculator. Second distribution, normal CDF. We're still staying between those two bounds. Lower is 440, upper is 455. The mean is going to stay the same. We found here that the standard deviation for 36 for our n is going to be a 2. I update all that. I paste it in, I hit enter, I see that my percent here is 99.38%. Okay, so let's move it over here to the board, put it all up so you can see it nice and neat. Put it on the board. D, X bar is approximately normal, 450 and 2, just like from C. Okay, that's our distribution. That's how it's distributed. E, probability statement. 440 is less than or equal to X bar is less than or equal to 455. Calculator statement, normal CDF, 440, 455, 450, and 2, just like what we typed on the calculator. Put it in a sentence with our percent. Probability that the average weight of 36 randomly selected trout is between 440 and 455 grams is 99.38%. That's it. Simple as it gets. Question number 3. The statistics department has found that the average grade on the final exam for its introductory course is 74.8 with a standard deviation of 8.2. Suppose a particular class of 32 students is considered typical of those taking the course. Determine the probability that their average score on the final examination, and then we'll go into the questions. The first thing it asks you for is the distribution. Next thing we look at is for part A, it says, will it exceed 76? Proper notation is important. And B says, will differ from the mean by 2 points or less, which means that it'll be between that 72.8 and that 76.8. Let's go to the board and solve question number 3. Alright, so we look at the distribution. X bar is approximately normal, 74.8, with a standard deviation of 8.2 over the square root of 32. Now, like we said, 32 is greater than 30, therefore we don't have to know that the initial distribution is approximately normal. We just have to assume that everything's chosen randomly and independently. Hopefully it is here. It's something we can't control. So the mean never changes. The standard deviation, if you've got a size n, you need to put it over the square root of that n. Okay, you can reduce this. You could pull a 4 out of that square root, and the square root of that 4 is going to be a 2, and then you could kind of simplify from there. Or you could actually pull a 16 out of that one, so you'd have 4 square root 2. You could do that if you wanted to. I know you're just going to type it on the calculator anyway, so unless it's really easy to simplify, like if it's a perfect square, don't worry about it so much, just worry about getting to the right answer. That being said, if you have to type it on Pearson, they're probably going to want you to simplify it as much as possible. Okay. A, remember we said probability that X bar is greater than or equal to 76, or strictly greater than 76. To type it on the calculator, normal CDF is what we're using. 76 is our lower bound, because it has to be greater than 76. Remember we used that 1e99 function to represent infinity. So we're looking at 76 or greater. So this is our representation of infinity. Mean of 74.8, standard deviation of 8.2 divided by the square root of 32. You type that all in on your calculator, you should get 20.39%. Easy enough, right? Here we wanted to find the probability that it was within 2 points of either side. So between 72.8 and 76.8. We type it into our normal CDF. 72.8 is our lower bound. 76.8 is our upper bound. Our mean stays the same, 74.8. Our standard deviation, 8.2 divided by the square root of 32. Type it directly in your calculator like that, you'll get 83.23%. That simple. If you want to look over here at the calculator really quick, just to show it to you, you can see right here, normal CDF, 76 one, normal CDF of the 72.8 one, and if you wanted to look at it, if you wanted to look at that one again, you could see that it's all typed in correctly right there with the mean and the standard deviation. You can try it on your own calculator. You will get both of those percentages. Number 4 says a restaurant is interested in the amount of time its customers spend dining in so that they can be more precise when taking reservations. They find that customers spend an average of 40 minutes dining in. If the standard deviation is 12 minutes, what is the probability that a sample of 50 customers will spend? And then we have 3 follow-up questions along with a question about the distribution. So we will write the distribution on the board. Question A says an average of less than 38 minutes dining in. Question B says an average of more than 45 minutes dining in. And question C says an average of between 38 and 45 minutes dining in. Okay, so let's go to the board real quick, solve all these out. Alright, so we needed to figure out what the distribution was. We had a sample size of 50, so I don't need to know any information about my initial sample, whether it's normal or not. Because the sample size is greater than 30, I can say it's normal. I just have to keep my conditions that it's randomly selected and they're independent. The mean stays the same, so X bar is approximately normal, mean of 40, standard deviation. You write the standard deviation 12 on top, divide it by the square root of n, and that's your new standard deviation. A, the probability that X bar is less than 38. So, I've got normal CDF in my calculator. My lower bound, if it's greater than or less than 38, is negative infinity. So I use the negative 1E99, upper bound's 38, my mean is 40, my standard deviation we found to be 12 over the square root of 50. If you type that in, 11.93%. B, probability that X bar is greater than 45. Normal CDF, 45. 1E99 is my upper bound, greater than 45. Lower bound is 45, upper bound is infinity. Mean stays 40, standard deviation still the 12 over the square root of 50. If you type that in your calculator, you get 0.16%. Answer to C. Probability that 38 is less than or equal to X bar is less than or equal to 45. So we were looking between those two bounds on that one. Normal CDF, 38 is my lower, 45 is my upper, my mean is 40, my standard deviation is 12 over the square root of 50. If you type that in, you get 87.91%. Once you get these, they roll out really, really fast. You find your bounds, you find how it's distributed. The hardest part is to remember what the standard deviation is. If you can get the standard deviation right, and you can type in your calculator right, you should be good to go on finding these percents. In the first part of this lecture, we did the central limit theorem for population means. Okay, sometimes we don't have the mean. Sometimes it's given to us in proportions. So what we're going to look at now is population proportions. So population proportion, which we're going to denote by P. We've been using X bar for the means. We're going to use P for the proportions. That's going to be our parameter. Alright, so the population proportion is a parameter that is simply the percent of the population that exhibits a given characteristic. The statistic that is used to estimate the population proportion is P hat, called P hat. That little triangle or little emblem up here is just a hat, so we call it P hat. P hat equals X over N. X is the total number of items in the sample with the given characteristic. N is the total number of values in the overall sample. Think about it like this. You got 100 marbles. Half of them are blue, half of them are red. So you've got 50 over 100 would be your percent of blue marbles, and 50 over 100 would be your percent of red marbles. Just like we've done with P and Q before, P is 1%, Q is just 1 minus that percent. So if P is 70, your Q would be 30. We'll do some examples on the board, don't worry. We will show you all that. We can apply the central limit theorem to the distribution of P hat with a couple of additions. So, one, we have to have a 10% condition. Our sampling is less than 10% of the population. Okay, so as long as we're sampling less than 10% of the population, we're good. The second condition, sample size. If N times P is greater than or equal to 10 and N times Q is greater than or equal to 10, then the sample size is large enough to say that P hat is approximately normal P, comma, square root PQ over N. So that would be your mean, that would be your standard deviation. Okay, so essentially we can't be too big. We've got to be less than 10%, but we also can't be too small. This N times P and this N times Q have to be greater than or equal to 10. So as long as we're between those two conditions, we can say that our P hat is approximately normal with a mean of P and a standard deviation of the square root of PQ over N. Okay, let's look at some examples. The first example here says, a study shows that 30% of people in a relationship with someone who smokes cigarettes, who themselves do not smoke cigarettes, still wind up with cancer relating to the inhalation of cigarette smoke. A random sample of 50 people whom spouses smoke but they do not is taken and checked for both past and current cancers relating to the cigarette smoke inhalation. What is the probability that less than 27% of these people have or have had cancer? Okay, so we need to tell what P and P hat represent in this problem. So P is our overall proportion. P hat will be our sample proportion. So we want to know if this sample of 50 people right here is going to wind up being less than that 27%, even though the regular sample P is right at 30. That's pretty straightforward. Justify that using a normal curve to approximate this probability is appropriate. If so, give the distribution. Alright, now here's where we can go to the board. Let's see. C says give the sampling distribution of P hat using the proper notation. We'll do that as well. Let's go to the board real quick and put this up. Alright, so we've got that our P is 0.3, our N is 50. One of the things we need to check is the 10% condition. Okay, 10% condition, if they don't give you the overall number that's in your population, sometimes you just have to conceptualize it. It didn't tell us how many people were in our population that we were looking at here. But what we are looking at are people who have gotten cancer who didn't smoke, essentially. You got to think that the overall population is probably much, much greater than 50. Okay, for it to be 10% or less, then N would have to, or our overall population would have to be greater than 500, right? Because 10% of 500 is 50. You got to think there's more than 500 people that have had a cancer like that who didn't smoke. So does our 10% condition hold? Yes, it does. NP and NQ greater than or equal to 10 are a lot easier to check because you have hard numbers to look at most of the time. So we've got N here is 50. Our P here is 0.3. 50 times 0.3 is 15. Is 15 greater than or equal to 10? Yes, it is. Here we've got 50 times our Q here. Remember, come over here. 1 minus P equals Q. 1 minus 0.3 equals 0.7. So our Q here is 0.7. 50 times 0.7 is 35. Not 0.35, it's 35. So that one works as well. What you'll notice with this rule, if you check the smaller percent out of the two and it works, the other one's going to work. Still need to check both for most people, but if you see what I'm talking about here, if you check the smaller percent, which isn't necessarily always P, which isn't always necessarily Q, then if the smaller percent works, the bigger percent's going to work. So these conditions hold. So since those conditions hold, we can say that the sampling distribution of P hat is approximately normal, P, which is 0.3, and then we've got that square root of P times Q. Our Q here is 0.7 all over our N, which is 50. Okay? You can simplify that if you want to. You can type that directly in the calculator if you want to. I'm just going to leave it as is. So we've got P hat's approximately normal, 0.3, square root of 0.3 times 0.7 all over 50. Alright, part D says write the probability statement dictated by the problem, give the calculator command, and the solution to the problem for part E. So the problem said that 27% or less than 27% of these people in our sample actually had this situation. So what we're looking at here, we've got the probability P hat is approximately normal 0.3, square root 0.3 times 0.7 all over 50. So we can use that for our normal distribution down here. We write our probability statement for part D. Probability that P hat is less than 0.27. You can write 27% if you like. I'm just going to use the decimal 0.27. E. We're going to write the calculator command, normal CDF, just like we've been doing the entire chapter. Our lower bound here, we're looking at less than 0.27, so we're going with negative infinity. On up to 0.27. Our mean here is our 0.3, straight from our distribution. Our standard deviation is that big square root. So square root 0.3 times 0.7 times 50. If we type that in our calculator, we get 32.17%. So I'm going to show you the calculator so that you can see. Some of you really like to see it typed in the calculator. So your lower bound's -1E99, your upper bound is 0.27, your mean is 0.3, and your standard deviation is 0.3 times 0.7 divided by 50, all underneath that square root. If you hit paste, enter, you get that 0.3217 or 32.17%. Example number 2, the National Fire Protection Association reported that 14% of home fires resulting in at least one fatality are caused by faulty heaters. An insurance company sampled 80 reports of home fires resulting in at least one fatality. Tell what P and P hat represent in this problem. Okay, P is at 14%. P hat is the sample proportion of what we wind up taking. Our sample here is 80. So P hat represents that proportion of people within those 80 that wind up with a home fire resulting in at least one fatality. Okay. B says justify using a normal curve to approximate this probability is appropriate. So what we're going to do for B, we're going to show all of our steps here. Is it independent? Is it random? Do we have the less than 10% condition? Is NP and NQ both greater than or equal to 10? And if it is, we're going to give the sampling distribution of P hat using the proper notation. So let's do that on the board real quick. Alright, so we're going to answer this question. First off, we need to see that our N is 80, our P is 0.14. I'm going to go ahead and find our Q. So our Q is 1 minus P. 1 minus 0.14 should give me 0.86. So our Q here is 0.86. Alright, so if we look at our conditions, one, it has to be independent. So each of these fires that resulted in a fatality has to be independent of each other. I believe we can assume that. Hopefully there wasn't just like a one fire that leads to another fire that leads to another fire, etc., etc., etc. There's nothing we can really do in this case to manually or ourselves control the independence. So we got to believe that it was done independently. Same thing for random. So we've got to assume that all these houses that burned up and resulted in a fatality were done randomly. Hopefully we don't have none like a serial arsonist or whatever going around actually setting these fires, knowing it's the specific insurance company, etc., etc. So we're going to assume these conditions hold. The less than 10% condition, okay? I don't know how many houses have burned in the entire U.S. or the whole world due to faulty heaters, but I gotta guess that it's probably more than 800, because if it was 800, 80 is 10% of 800. I gotta guess that it's probably happened more than 800 times throughout the entire history of the whole U.S. world, however you want to take it with the percent of the problem. So I'm going to say the 10% condition holds as well. We can get into some concrete numbers here. We've got NP greater than or equal to 10 and NQ greater than or equal to 10. So NP, our N here is 0.14. Our P is 0.14. Our N is 80. Doesn't matter the order because we're multiplying. 0.14 times 80 should give me, let's see, 0.14 times 80 should give me 11.2. So it's close to 10, but it's over 10, so we're good on this one. If this one holds, I promise you this one's going to hold, because 0.14 is a whole lot less than that 0.86 times 80. 0.86 times 80, what we wind up with is 68.8, which is definitely greater than or equal to 10. So all of our conditions hold. We need to write the sampling distribution of P hat. So P hat is approximately normal, 0.14. Okay, now we've got to have that big square root. We've got 0.14 times 0.86 all over 80. So our P hat is normally distributed, 0.14, square root of 0.14 times 0.86 divided by 80. Alright, let's look at D. What is the probability that more than 17.5% of fires in these reports were caused by faulty heaters? It wants the probability statement, the calculator command, and the answer in a complete sentence. Alright, so let's look at it. The probability statement. Probability, P hat, greater than 0.175. Okay, you can write that as 17.5% if you'd like. That's fine. Don't have a problem with that. Calculator command. Normal CDF. Okay, is greater than 0.175, so our lower bound is 0.175. Our upper bound is 1E99. That's our infinity. Our mean here, we said before in our previous question that our mean was 0.14, and our standard deviation was the square root of 0.14 times 0.86 all over 80. So that's the standard deviation you got to use. If we type that into the calculator, we get 18.35%. I'll show it to you briefly here in a second. If I want to write this answer in a complete sentence, it says the probability that more than 17.5% of the fires were caused by faulty heaters is 18.35%. That's simple. Now if you want to see the calculator command, pull it up for you real quick. So, calculator command, second, distribution, normal CDF. Just type it all in. 0.175, 1E99, 0.14, square root 0.14 times 0.86 divided by 80. Hit paste, hit enter. You get 18.35%. Easy enough. Now let's look at this next question here. Okay. Part E. It says, what is the probability that between 12.5% and 20.8% of the fires in these reports were caused by faulty heaters? So let's go to the board and do this one. Alright, so our probability statement for this one. Probability that is between that 12.5 or 0.125 and is less than 0.208. So you just got to bound that p hat. This is our probability statement. Calculator command, normal CDF. Lower bound is 0.125, upper bound is 0.208. Our mean is 0.14. Our standard deviation is that big square root. Square root 0.14 times 0.86 divided by 80, just like it was in our other one. That should give us, if you type it in your calculator right, 61.07%. So if I want to answer it in a complete sentence, the probability that between 12.5% and 20.8% of the fires were caused by faulty heaters is 61.07%. Alright, question 3 says, information on a packet of seeds claims that the germination rate is 92%. What is the probability that more than 95% of the 160 seeds in the packet will germinate? Does this problem meet the criteria to use the normal distribution? Okay, so let's take it to the board. Alright, so we've got to see if we can use a normal distribution for this. So, independence, random, they probably both hold. I don't see anybody specifically going in and somehow specially picking out specific seeds for a certain person to get in a specific package. We've got to check the 10% condition. We've got 160 seeds in this packet. That's got to be less than 10% of the population of seeds at the seed distributor. And there's got to be hundreds of thousands, if not millions of seeds there. So 160 is really, really small compared to that. That holds. Let's check NP and NQ greater than or equal to 10. So, N is 160, P is 0.92, multiply those together, I get 147.2. Is that greater than or equal to 10? Why, yes it is. N times Q, 160 times 0.08. Remember to get Q, we do 1 minus P. 1 minus P is your Q, so 1 minus 0.92, that gives us that 0.08. 160 times 0.08 is 12.8. That is also greater than or equal to 10. So it works. Alright, so let's go ahead and figure it out. So, because it's that way, I can say that p hat is approximately normal. Mean of 0.92, standard deviation of 0.92, square root of 0.92 times 0.08 all over 160. If I want to solve the problem, so the problem says, what's the probability that p hat is greater than 95%. Okay, that means I need to do normal CDF 0.95, okay, 1E99, and then my mean here is 0.92. My standard deviation is the square root of 0.92 times 0.08, all divided by 160. So if I go and I type that in on my calculator, what I'm looking at, second distribution, normal CDF, get it all typed in. let's see, 0.95 is your lower bound. 1E99 is your upper bound. Get your mean and your standard deviation typed in. You should wind up with 0.0809, okay, which is 8.09%. Easy enough. Number 4 says, it's believed that 4% of children have a gene that may be linked to juvenile diabetes. Researchers are hoping to track 20 of these children for several years. They test 732 newborns for the presence of this gene. What's the probability they find enough students for their study? Does this problem meet the criteria to use a normal distribution? If so, we're going to solve it. So, let's go to the board real quick and find out. Alright, so we want to know if we can use a normal distribution. So, are they independent? Are they randomly chosen? I'm sure those both hold. There are a lot of people with juvenile diabetes, believe it or not. And if we're only choosing 732 of them out of the entire world, I have to believe that there is more, way more than 732, right? I believe that 732 is way less than 10% of the overall world population of children with juvenile diabetes. So all those conditions hold. The main ones we really have to check here are the NP and NQ and see if they are greater than or equal to 10. So 732 times 0.04 should give us 29.28. 29.28. If that one holds, this one's going to hold because 0.04 is smaller than 0.96. But we'll do it just to see and show you. So this one is 702.72. Both of those are greater than or equal to 10. So that condition holds. Since that condition holds, I can say p hat is approximately normal. Mean of 0.04. Standard deviation is the square root of my p, which is 0.04, times my q, which is 0.96, all divided by 732. Remember, you get your q by 1 minus p. Now let's go ahead and solve the problem since we've got it up. So, this one's a little tricky because it doesn't give you the percent straight out. You have to find it on your own. So, it wants to know, if you're looking at your question, it wants to know the probability that they will find enough people for their study. They need at least 20. They want 20, right? So, if they get more than 20, fine. They can choose out of that. However many they get, they can pick 20 of them. But they have to have at least 20. So, we look at the probability statement here. The probability that p hat is greater than or equal to 20 divided by that 732. We're working with percents here, okay? The biggest mistake I see with these is people, instead of doing it as 20 divided by 732, they'll put it as just 20. P hat is a percent. It has to be a percent or a proportion right here. It can't be a whole number unless you're doing like 1. And we're not ever going to find 100%, right? That percent is probably going to be 0. So it's always going to be a percent or a decimal right here when we're talking about p hat. If we're talking about x bar, whole different story. If we're talking about p hat, it has to be a percent or a proportion here, okay? So we type it in our calculator. We want it to be greater than or equal to 20 over 732. So lower bound, 20 over 732. Upper bound, 1E99. Our mean here, 0.04. Our standard deviation, square root of 0.04 times 0.96, all divided by 732. You type that in your calculator, you should get approximately 96%, right? It'll be 0.9599 something, something, something. It rounds up to 96%. So there's a 96% chance with a sample size of 732 that they find at least those 20 children that they need to do their research study. Question number 5. It says a certain insurance company insures homes in Tornado Alley. Of the 31,000 homes they insure in that area, 30% of them are stick-built homes while the rest are mobile homes. Samples of 100 homes are selected at random after tornado season to see if they survived. Does this problem meet the criteria to use a normal distribution?
And then B, C, and D will answer all those at the same time too. What proportions of the samples will have more than 36% stick-built homes? What proportions of samples will have less than 29% stick-built homes? What proportion of the samples will have between 25% and 35% stick-built? Okay, let's take it to the board. All right, let's answer this question. First one, we got to decide if we can use the normal distribution. So, is it independently chosen? Is it randomly chosen? Let's hope so. Something we can't control. Let's check the 10% condition. We actually have hard numbers to check this with. They have 31,000 homes that they insure. Okay, we're doing a sample size of 10%, or we're doing actually a sample size of 100. We need to see if that is less than 10%. 31,000 times 10%, which is 0.1, is 3,100. Okay, 100 is less than 3,100. Therefore, the 10% condition holds. Okay. We also need to check that NP and NQ are greater than or equal to 10. 100 times 0.3, that is greater than or equal to 10. That works. 100 times 0.7, that's greater than or equal to 10. That works. So now we can say P hat is approximately normally distributed 0.3 square root 0.3 times 0.7 all over 100. Okay. If we go to answer question B, the probability that P hat is greater than 0.36. Normal CDF. 0.36 is our lower bound. Means our upper bound is 1E99. We have a mean of 0.3, a standard deviation of 0.3 times 0.7 divided by 100. If you type it correctly in your calculator, you should try it on your own, you should get 9.52%. C, it says what's the probability that less than 29% or stick-built homes. So we're going to do normal CDF, negative 1E99, 0.29, 0.3, square root of 0.3 times 0.7 all over 100. That should give you, if you type it in your calculator correctly, 41.36%. D, probability that they're between 25 and 35%. Okay, so we got our probability statement. These, that should have a hat on it. Normal CDF, 0.25 is our lower bound, 0.35 is our upper bound. Our mean is 0.3. Our standard deviation is the square root of 0.3 times 0.7 divided by 100. We should get 72.48% if you type it in your calculator correctly. If you have any questions with these, you have to email me and let me know. But hopefully this is really straightforward. Percents really shouldn't be that bad. They follow the same outlines as means. You just have to make sure you actually have percents. Alright, E says what's a sampling method we can use in order to ensure that there are exactly 30% stick-built homes in each sample? It's a flashback. We did this earlier in the semester. It should just be stratified sampling. You should know that. That's something you just got tested on. So that's just a flashback. Make sure you still remember that material. F. After sampling, it was found that 67% of stick-built homes sampled survived, while only 42% of the mobile homes survived. Can we model survival percentage of stick-built homes as normally distributed? And can we model survival percentages of mobile homes as normally distributed? Okay, so let's go to the board real quick and see. So, we know that we have to check one that is independently done and is randomly chosen. We're going to assume all of that was done correctly. Let's look at the 10% condition first. So, if we're looking at stick-built homes, we got to find our sample can't be any larger than 10% of those stick-built homes. Okay, there's 31,000 homes total that are insured, but only 30% of them are stick-built homes. That gives us 9,300 stick-built homes that are insured. We want 10%, or we actually want less than 10% of those to be sampled. So 9,300 times 10% gives you 930. So as long as this N here is less than 930, then we're okay. Okay, we can say it's normally distributed. The other condition we have to check NP and NQ are both greater than or equal to 10. Okay, so if I look at it, N times 0.67 has to be greater than or equal to 10, because 67% of the homes in our situation that were stick built survived the tornado. Okay, so all I do here is divide 10 by 0.67 and I get 14.93. So as long as n is greater than 14.93, this condition holds. If I look at q, n times q, q here is 0.33 because 1 minus p is our q. If I back solve for n here, then I get n is greater than or equal to 30.3. All I did is divide 10 by 0.33. Okay. Now I've got to pick one of these. Okay. And that's got to be my lower bound for my n. And as long as n is between these two bounds, then we're okay and we can say it's normally distributed. If it's not within those bounds, it can't be normally distributed. Okay. The reason I picked 30.03 is both of these have to hold. Okay. This one's not going to hold at 14.93 because it has to be greater than or equal to 30. So I have to choose the bigger one here. So as long as n is between 30.3 and 930, we're okay and we can say yes indeed it is normally distributed. But this has to hold in order for that to be the case. So our sample size has to be somewhere between, we can't sample a half of anything, so basically somewhere between 31 and 929 because we are strictly less than that 930. Alright, if we look at mobile homes, we'll do it the same way. 10% condition, 70% of the insured homes are mobile homes, so 7.7 times 31,000 gives you 21,700. I want to take a sample of less than 10%, so my 10% condition will hold. So my sample size has to be less than 21,070. So we've got that as our lower bound for our n. Now, we have to check that NP and NQ are greater than or equal to 10. Okay? My P here is 0.42. So n times 0.42 has to be greater than or equal to 10. All I'm doing here is back solving for n. So I'm dividing by 0.42 here, dividing by 0.42 here. And I get that n has to be greater than or equal to 23.81. Same thing here. Okay, my q is 0.58. So n times q greater than or equal to 10. I'm going to divide by that 0.58. And I get that n has to be greater than or equal to 17.24. Like I said, both of these conditions have to hold. This condition is not going to hold at 17.24, so I have to go with the bigger one. So as long as n is greater than or equal to 23.81 and less than 2,170, I can say it's normally distributed. Any other numbers, and it won't be normally distributed. This has to hold. Like I said, n has to be a whole number, so it has to be somewhere between 24 and 2,169. That's it. That's all I've got for you today. We'll do another one of these video lectures for the next class for Chapter 18. You do have a quiz for Chapter 17 uploaded. Please be honest in taking everything. If you have any questions at all, please shoot me an email ASAP. I'll try to be extremely responsive as quick as possible as soon as I see it. Other than that, hopefully this worked well for people. Pause at any point you need to pause. If something doesn't make sense, send me an email. Other than that, bear with me. I'm doing the best I can with what I've got. If you really don't like something or something's really not working for you, let me know. If you really do like something and you're like, hey, that really worked, can you do stuff more like that? Let me know, and I'll try to kind of cater to everybody who wants and needs as best I possibly can with the limited resources I have here at my house. Other than that, y'all stay safe and see you again on the next lecture.